Welcome! Everything around us, the air we breathe, the water we drink, even you and me, it's all made of these tiny, totally invisible molecules. So the big question is, how in the world do we study something that's way too small to ever see? Well, let's dive right in and find out.
So, we're going to go on a little investigation together to uncover the secret life of a molecule. We'll start with a quick tour of their world, then we'll get into their size, how they play with light, how they move, how they share energy, and then, at the very end, we'll put all the pieces together for the complete picture.
To really understand a molecule, scientists can't just ask one single question. They have to ask a whole bunch of them. It's kind of like using all the different tools in a toolkit to build a really detailed picture of something you can't actually see with your own eyes.
All right, let's kick things off with a pretty basic question. How much space does a whole bunch of molecules actually take up? In the world of chemistry, there's a name for this. It's called molar volume.
Now this is where it gets really interesting. This slide shows us a kind of universal rule. See, for any ideal gas, it doesn't matter what it is, oxygen, helium, you name it. If you have a specific number of those molecules under the same conditions, what we call standard temperature and pressure, they will always occupy the exact same amount of space, 22.4 liters. It's like a magic number for gases.
Okay, so we've got a sense of their size, but molecules aren't just sitting there in a box, they interact with things. So what happens when we shine a light on them? Or what if we put them in, say, a magnetic field?
Check this out. This shows us something absolutely fascinating. A molecule's shape completely changes how it behaves. On the left, you've got a lactic acid molecule. Because its shape is asymmetrical, it's a little lopsided, it actually twists the light that passes through it. But look at the tartaric acid on the right. It's perfectly symmetrical, so the light just goes straight through, no twisting at all.
So it really all comes down to one simple thing, symmetry. That's it. If a molecule has a perfect line of symmetry, kind of like you could fold it in half and the two sides would match up perfectly, it's considered optically inactive. But if it's lopsided, with no way to mirror itself, then it's active, and it's going to twist that light.
And get this, it's not just about the molecule's own shape. Outside forces can get in on the action too. As you can see here, if you stick molecules inside a really powerful magnetic field, that field can also make the light rotate as it passes through. This is called the Faraday effect, and it's another one of those key clues scientists use to figure out what a substance is all about.
Now let's keep building on this. Molecules aren't just sitting still waiting for something to happen. No way. They are in constant motion. They're wiggling, they're spinning, zipping all over the place, and all of that movement, well, that's a form of energy.
A simple way to think about a molecule's energy is to break it into two parts. First, you've got kinetic energy. That's its moving energy. Then you have potential energy, which is like the stored energy tucked away in its chemical bonds. Add those two together, and you've got the molecule's total energy. So, to keep track of all this zipping and wiggling, scientists talk about something called degrees of freedom. Now, I know that sounds super complicated, but it's really just a fancy way of counting all the different ways a single molecule can move around. That's all it is. And this slide, it just perfectly breaks down those main dance moves. First, you've got translational motion. That's just moving from point A to point B. Then there's rotational motion. Yep, that's just spinning. And finally, you have vibrational motion, where the bonds between the atoms are stretching and bending, kind of like tiny springs. Okay, so we know that molecules have all this energy, and it's tied up in all these different kinds of movement. But here's the next question. How is that energy divided up? Does one type of movement get more of the energy than another? You might think that maybe the zipping around part gets a bigger piece of the energy pie than the wiggling part. But it turns out nature has this surprisingly fair, really simple rule for how this works.
And here it is. This is called the principle of equipartition of energy. Now, what a mouthful, right? But the idea itself is really simple. It just means that, on average, every single one of those dance moves, every single degree of freedom gets the exact same slice of the total energy pie. It's totally fair.
So what is this magical equal share? It's this little value right here, 1/2 kT. Now, K is just a constant number, and T stands for temperature. So this tells us the specific equal amount of energy each type of movement gets. And it's all based on how hot things are. Every wiggle, every spin, every zip. They each get their fair share. It's perfectly balanced.
So now that we've gathered all of our clues, we know how much space they take up, how they dance with light, how they move and share their energy. Let's zoom out and take a look at the complete portrait of a molecule that we've managed to build. And this is it, The whole shebang. We started with a simple question about volume, and from there we branched out to look at light, energy, and motion. You can see right here on this map how all these different properties connect right back to that one central molecule, telling one complete, super detailed story. This is how scientists make the invisible world visible.
You know, understanding these fundamental rules isn't just about passing a test. It's the very foundation that lets us do amazing things, like design new materials, create life-saving medicines, and invent incredible new technologies. So I guess the big takeaway is, by asking these simple questions about the smallest things we can imagine, we learn how to change our world in the biggest ways. Which really makes you wonder, what do you think we'll discover next?